Hello and welcome to today's webinar presented by Dlubal software. Today we'll be working in our structural analysis and design software, Rstab and Rfem. The topic for today's webinar is tips and tricks for modeling in Rstab and Rfem. My colleague Wieland Gotzer will be your presenter. He's a product and customer support engineer located in our Leipzig, Germany office. My other colleague, Sina Gebhardt, will be your moderator, answering any questions you may have. She's a product and customer support engineer, also located in Leipzig, Germany. And finally, my name is Amy Heilig. I'll also be a moderator. I'm the CEO of the U.S. office located in Philadelphia, Pennsylvania. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the webinar. You can do so within the same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. And with that said, I want to go ahead and turn it over to my colleague Wieland for the rest of today's presentation.
All right, thank you very much, Amy, for the introduction. Let me just check if you can see my screen. Yeah, that's fine. Today we have three topics, and we're going to start with the first one in Rstab. This is how you can detect and fix modeling errors and instabilities. We will also continue in Rfem with one or two small examples for instabilities, and after that we will check how you can connect members and surface elements properly. And in the last part of the webinar, I'm going to show you how to model nodal constraints, nodal releases, line and surface releases. So with that said, we can just go on to the Rstab, our framework program. And this is just a very small example framework. You can see I have defined some bracings over here. And you can see that these are member type tension. That means if they're going to have compression forces, they will be removed in the calculation. We have also some hinges, but in global Y direction, this is a rigid frame. So I will just try to calculate the self-weight load case, and as you can see, the model is unstable in node number 17. We have a free rotation about the y-axis, and I said that the model is actually fixed in the y-axis. No, it's a free rotation about the y-axis. It's not movable in y. So for the y-axis, for the x direction, we actually have to find the bracings. And the question is why the model is still unstable. So this is a very common case of tension members. And you can imagine if you have self-weight load case and you calculate the first iteration, probably all the tension members, they have compression. And in the calculation, they will be removed in the very first iteration at the very same time. And if you imagine this exact structure with all of the tension members, let me just remove them, it's gonna fall aside, and yeah, that's the instability. Yeah, how you can fix it? We have some nice tools for you in calculation parameters. Calculation parameters over here, and in the middle you can see we have reactivation of failing members, and on the bottom you can see exceptional handling. And this option allows you to handle the failing elements like these bracings in two ways. You can assign a reduced stiffness to the failing members, or that's my favorite option, to remove them individually during successive iterations. I will try the first option, and you can see that in in the end, the calculation was successful. And we have still 2 tension members working in this structure. And this leads to the final results. What you have to take care about is that if you have a structure with, let's say, 150 tension members, you probably have to increase the number of iterations in the calculation parameters. So if like 110 tension members are failing, you should have at least 111 iterations. Yeah. Let's also try the second option over here, assign the reduced stiffness. That means if you have a tension member in compression, the program will assign a reduced stiffness by a factor of 1000. So we can also try this option, run the calculation again, and it's fine. You can see that now all the members are working, all the bracing members with views members by type. No, that's not beam. Let's just select the bracing members, select special member with type tension. Visibility, like here you can see that all the tension members are still in the structure. Yeah, that means they just have a reduced stiffness if they have some compression. And both of the options in this example lead to final results. And with that said, we can just continue to the next example. Let me just give you one extra information. For the bracings, if you have like cables, you could also add initial pre-stress to stabilize them. Yeah, in this case, we have angles, and I wouldn't add a pre-stress in this case, but if you have cables, usually you will add also a member load as initial pre-stress. Okay, let's go on to the next example. That's framework number 2. It's like the same framework on the left side and a smaller one on the right one, and these should be connected with these with this like cable duct, and you can just try to calculate the self-weight load case. And as you see in the graphic, the deformation looks quite strange. It looks like the cable duct is actually not connected. And yeah, what's the reason for that? We have some tools where you can find out the reason for these strange behavior over here. You can access this with tools. You will find model check, and there you will have 4 options like overlapping members, crossing unconnected members. That's not the case in this model, but we have independent systems and identical nodes. I will start with the independent systems check, and you can see that we actually have 2 independent systems, like the left side and the right side. So the question is, what's the problem in the connection? And we can check it with tools, model check identical nodes. And there we have 4 groups of identical nodes. That means nodes which are closer than this tolerance. If you can't find a group over here, you can also adapt the tolerance, but in this case, the nodes are so close to each other that even the tolerance of such a small value is enough to check it. Yeah, you get a information arrow in the graphic, and if you zoom in, it still looks connected, but in the end, you can see that there's a problem. These are not connected, and I can just like drag and drop this one, or you can use the check again with tools model check identical nodes. Now I have 3 groups left, and you can select what's going to happen with these nodes. Nothing. That's not the solution. We want to unite the nodes. Okay. We can run the design the calculation again, and now we have just 1.4 millimeters, and that's fine. So let's move on to our finite element program Rfem to check also other types of instabilities. There we have a 3D framework, self-weight in the calculation parameters. Because I have also tension bracings over here, I already activated to remove the failing elements in specific iterations. And I will just try to calculate the model, but it's completely unstable also in the self-weight load case. And in the text, you can see some additional info that also with the additional module RF stability here, you can check the reason for this instability. Yeah, and that's what we're going to try now, because you can see the red arrows over here that there's a problem, but actually that this is a truss member, this is a truss member, but this is rigid. There shouldn't be an issue over here. Yeah, so the red arrow in the graphic isn't always the reason for the instability, and therefore just take a look at the RF stability module. If you have some results, you can check eigenvectors and eigenvalues with the module, but we don't even have the results of one single load case. So what I want to find out is the eigenvector of the unstable model. That's what needs to be activated over here. We can calculate the eigenvector, and you get a lot of zeros because it's an unstable model. Also over here we get some deformations, but it's not so useful. We just need to take a look in the graphic, and yeah, we actually have a problem with this frame, and you can see that there are some hinges that might cause a problem. As you can see, yeah, there's a hinge, and this one is also hinged, and I need to remove these two hinges. So just double click on the taper on the left side, remove the hinge. Okay. Remove the hinge also on this side. And now we can just try to run the self-weight. Some iterations for the bracing members probably. And now it's fine. Yeah. We can also check the critical load factor now in RF stability. We don't have an unstable model at the moment, so let's check the critical load factor. Oh, that's still some problem in this calculation, but anyway, we can also check in the next model. Okay, so with the RF stability module, you can also find out the reason for the instability, and you can adapt the model because you can see the reason probably in the graphic. Yeah. So at the moment, we can just go on to the next model. That's the platform model over here. Still a framework. We have some bracing members, truss members over here. Tension members with some pre-stress assigned. And we have some surface loads applied on the members. And what we want to try is, yeah, we will just try to run the calculation, calculate all. So the load cases, they look pretty good, but as you can see, the load combinations, they probably don't get a result over here. So we have a problem in the load combinations. So if you have an instability like this, in fact, the you have to think like, what's the difference of the load combination to the load case? And the load case, when you, we have maximum displacement warning. In the self-weight, we can check. The self-weight is according to linear analysis. That means first order theory, and the load combinations, they are calculated according to P delta method. That means second order analysis. So the reason could be that I have a problem in the model itself, or the model is, let's say it's too weak. Maybe I have to change the cross section, because if the model is too weak, then you're going to have high deformations, and in the end it's going to be unstable. But if you calculate according to first order, then you don't calculate the results on the deformed shape, and that's the difference. So to find out, we will just try to calculate RF stability with the results of the first load case. That was the self-weight load case. So I will just select load case 1, the self-weight. I want to have 4 eigenvalues. I can just run the design. And there you see that you get some information. That's very interesting, because the critical load factor is the information that, for example, in load case 1, the self-weight, the critical load factor is below 1. That means the model itself, it can just take around 3% of the full loading. Yeah, and with this 3% of loading, it will collapse like this. So in this case, I could think like maybe over here I have a lot of hinges, and I will just try to remove these hinges, and then we will recalculate the model again. So let's switch off the results. I will rotate the view a bit, select the middle frame, and then right-click on one of these members. You get the information that you've selected 24 members, edit, and then we can remove all the hinges. Okay, delete the femesh, and let's try to recalculate, for example, combination number 1. Okay. And now it's like 2.8 millimeters, and it looks quite good. Yeah. So let's run the result combination, and the result combination contains all of the load combinations. And if these are fine, I think the model is good. Yeah, 25 millimeters. That's maximum. That's fine. Okay. Some additional information for the RF stability. If you check the critical load factor, like for example, combination 1, you get some interesting information if you have to calculate according to first or second order P delta. If you are doing a Eurocode 3 check, there's actually a formula that says that if your critical load factor is below 10, you have to calculate according to P delta or second order method. In this case, we have around 7, and therefore we have to calculate according second order theory. If this value is above 10, like the second one, we have a buckling of the inner column, then it would be okay just to calculate according to first order theory on the undeformed shape, because the bending moments won't change according to second order, and it's fine for first order calculation. All right, let's continue to the next model and the next topic. We want to check how to connect members and surfaces. like in this example, I have a 2D model. You can see it's just 2D, and there's this shear panel, and it's connected to a column, to 2 columns. Yeah. If you display a solid display model, you can see that actually the column is quite massive. And the question is how to connect this member to the column. In this case, I just it's just connected in this node, but we will take a look at the results now, and we will find out if this is a good solution. So already in the deformations, you can see that there's like a corner, and also in the bending moments of the column, it's not a real frame bending moment, it's quite too small. Yeah. And the reason for that is that the shear panel, it has 3 degrees of freedom, like translational deformations, but the column, it has also a rotational degree of freedom. And this is a incompatible femesh in this node. And we have to think how to connect the column with a rigid connection to the shear panel. And I will show you one solution. And for that, I will just copy the whole thing. One copy, and let's take a look. The dimension of this is around 7, so 7.5. So I will use 10 meter as a displacement vector. And the solution in this case, I will try to define a rigid member over here in this region to connect the column to the shear panel. So member type rigid is already defined in this case, and I can just define it by clicking in this area, and then I will just copy it one time like this, and the same thing on the other side, another copy from over there to over there. If you don't know the displacement vector, it's easy just to use this picking tool. Press the OK button, and that's fine. And we can just run the calculation again. And as you can see, I still have the bending moments over here, and there's quite a huge difference between the 0.45 kilonewton meters on the left side and the 4.67 or 66 on the right side. And also on the deformations, you can see that now there's a rigid connection between these 2 elements, the surface and the member element. So if you want to connect a member with the surface, you should think about this fact that there's on the left side, there's just a very, very, very tiny like area, or yeah, it's not a real area, but you have to think like how to connect this in a rigid connection from the member to the surface element. Okay. Now we will take a look at the last, no, not the last, but to the next model. Let me just delete the femesh. There we have like a small frame with some horizontal loading. And you can see in the deformations that yeah, of course we have some horizontal deformations, but what I want to do is I want to have like a surface in the area of this in the plane of these 3 elements, a rigid surface like a roof, like something like this. But I don't want to use a surface. I want to like connect these 4 nodes, that they are connected in a rigid connection. I want to use nodal constraint for this. And therefore, I can easily right-click on the nodal constraints in the data navigator, new nodal constraint. Yeah, it's quite easy. You have to select all the nodes you want to connect. This one, this one, and this one, 5 to 8. You can define according to the constraint plane, x, y, y, z, x, z. You can see that the constraint conditions are adapting automatically, or you can define your fully like manual constraint as you need. Yeah, I will just use the diaphragm constraint XY plane and press the OK button. You can see the constraint looks like this pink lines over there, and we can just recalculate the model. And now you can see we don't get horizontal deformations because these nodes are fully constrained in this plane. So in this case, we connected the nodes in a rigid way. In the next 3 models, we want to release something. So let's move on to the nodal release model. There we have, it's quite an easy example. We have 4 members and they are connected in this node. So as you can see, the members on the top, they have an eccentricity. I will just show you member eccentricity over there, and it's defined according to the relative offset of the cross-section. So if I would change the cross-section, it will also change the eccentricity in the model. And it looks like this. We have a timber element on the top and a concrete member on the bottom, and 2 forces like self-weight and 1 uplifting load case. And if I do it like this, I can just calculate the model. You can see that the elements are connected to each other also for the uplift. You can see in the member internal forces that there's a transfer of shear forces between the 2 elements, or the 4 elements in this case. And what I want to do, or what I want to model is, for the uplift, I don't want to have a transfer of the forces from the timber elements to the concrete. So it's only for the plus Z direction forces. For gravity forces, I want to have a connection, but for uplift, it's just lying on the concrete element and there shouldn't be a connection. And to do and to model this, we have nodal releases over here. Let me just change to the wireframe model and switch off the results. Nodal releases, new nodal release. Yeah, it's again quite easy. We have to select the node we want to release. That's just node number 1. We need to define a hinge. And in this case, let me just check which hinge to define. It's I want to use global hinges, UY, and this one is important, UZ, and also the phi X I want to release. And for the Z direction, it's important to have only a fixed connection, or a fixed connection if there's a positive force in this direction. So we will use fixed if positive PZ, and if it's a negative PZ, it's a release. Yeah. Okay. Then we have to choose the elements we want to release, and that's going to be the top elements. Press the OK button, and we can just run the calculation for the uplift again. as you can see, in the shear forces, there isn't a transfer of shear forces now. The concrete elements, they don't have any forces. Also in the deformations, you can see that these elements are not connected now. But for the gravity loads, if you recalculate the model, there should be a connection. Yeah, you can see the deformation is quite low. And also in the shear forces, we can see that there's a transfer of the loading. So for 1D elements, you can use the nodal releases over here. And now we want to take a look to the next dimension, to the line release. So that's basically the same, but with one more degree of freedom. In this case, we have a wall and a surface element. And if you calculate the self-weight load case, you can see that both of these surfaces, they are connected fully rigid in the corner over here along this line number 4. But what I want to do is I want to have a release, that there's no transfer of bending moments from this surface to this surface. And to model this, we can just change to data. And we want to have a new release, which is a line release. New line release, and along the line number 4, I guess, yeah. Line release type. We want to release for, of course, the rotation, px. And if you have a connection between these two surfaces, you can also define spring constants in the translational releases. Or if you have a partial activity, you can also use friction, a diagram, etc. In this case, we just keep it simple with a rotational release Vx. Okay, and we want to release one of these surfaces, and I will just choose the upper one, surface number 1. Okay, we need to delete the femesh. You can see the line release shown in the graphic, and I will just calculate the self-weight again, and you can see that there's no rotation or no bending moment transfer from this one or from this one to this one. Okay, so let's move on to the last example, which is this column foot over here. Let me just switch off the visibility mode. We have a column foot over here with the horizontal loading, and on the bottom, this isn't a member element. It's all made of surfaces, and on the bottom we have the foot is made of 2 solids. That's solid number 1, and we have another plate which is located over here, solid number 2. And at the edge of this plate, we have also surfaces, and this is like the weld along this plate. At the moment, it's fully rigid, connected, and we can just run the calculation of the horizontal load case. Yeah. Okay, so at the moment you can see we have around 1.2 millimeter deformation on top. Let's take a look at the column foot over here with the partial view. And yeah, we have no deformations at all. It looks like, yeah, of course, like these 2 solids are connected in every femesh node. And that's what I don't want to have. I want to have a release between the 2 surfaces or between the 2 solids if you have an uplift force. Because if you have an uplift force, then these forces should be transferred with the welds. And the question is how to release the two plates. Yeah. And this is what you can do with a surface release. That's the additional degree of freedom you will find in this list in the data navigator. Nodal release line, and now we have the surface release. Right click, new surface release. Which surface to choose? Let me just switch off the results, and we're gonna select the surface number 7. This one. We need to define a type of release. And we want to release all the degrees of freedom. And we again have a nonlinearity for the Z direction. And the Z direction should be fixed if you have a positive contact force, PZ. Yeah, if you have a compression force between the two solids, we want to have a connection. If you have uplift, then it should be released. Okay. And we need to release some objects, and this is going to be the solid number 2. Yeah, the upper one of the two solids. Okay. Just delete the femesh again. And now we can recalculate the load case and we will check the results. Just need a second in this case for the failing surface elements, I guess. But now it's done. So let's check the results now. And you can see that for the uplift, we have some deformations on the upper surfaces now. And that was quite a huge difference between, yeah, in this case, we have 0.10, 0.1 millimeter. But before it was completely rigid and there was exactly no deformation in this column foot. So you could see that the release is working now for the uplift, and we have a very different type of deformation now. So let's summarize the webinar at this point. At the beginning, we checked the instabilities in different models. You saw that you can choose between different types of exceptional handling for the failing elements in the calculation parameters, both in Rstab and Rfem. Next, I showed you how you can check the model. In Rfem, you can see you have also additional checks for overlapping lines, overlapping surfaces, etc. You can check identical systems, identical nodes, etc. And after that, I showed you how to define nodal constraints, and in the end, how you can release nodes, you can release lines, and you can release surfaces. With that said, I will just thank you for your attention, and I will give again the possibility to Amy to have some additional information for you.
Thanks, Wieland. We do know that was quite a bit of information, so we always want to encourage you to visit our website at dlubal.com. Here you can find much more information on both Rstab, Rfem, as well as our add-on modules. We also have many social media sites, so between these two and our website, you'll find access to videos such as recorded webinars, events and conferences when those will take place, knowledge-based articles, as well as upcoming webinars that will occur in the coming months. Our email for our German office is info@dlubal.com. Again, that's info, I-N-F-O, @dlubal.com. The phone number is +49 9683 92030. If you do have any questions or comments about today's webinar or anything else, feel free to either send us an email or give us a call. And with that said, we want to thank everyone for attending today. And as always, we hope to see you at our next webinar. Thank you.